Next speaker is Xiangji Huang, right? He's a first-year PhD student at Hong Kong University of Science and Technology. He has his master's on video streaming and is advised by Professor Zili Zhang. He focuses on real-time communication, which today he's going to talk about. Oh yeah, sure.
Thank you. Okay, so hi everyone. My name is Xiangjie from Hong Kong University of Science and Technology. So today I'm going to introduce our work on ACE. And this is the joint work of the Hong Kong USD and ByteDance. And we are improving the performance of the high-quality real-time communication. So it's for the RTC. It's kind of different from the first two speakers. We're not doing the VOD, and we're not doing the video streaming, but real-time communication. So just keep that in mind. So let's start. Firstly, let's talk about some background. Real-time communication, or RTC in short, is now taking like huge part in our daily life. It powers a lot of things, from like daily video calls, video conferences, to some cutting-edge applications such as cloud video gaming, or even future applications such as remote surgery. But what's unfortunate is that the tail latency issues are still holding back the path of some future applications. Here I list some of the papers that appears in the recent year top-tier conferences. They all have measurement on large-scale RTC applications. And the tail latency values shown in their studies are still very high. For example, this year we have a paper called Tooth in SDI-25. And the store frequency that reported by its best baseline is still have 1 store event per minute. So it means that every minute you will have sensed a noticeable 100 millisecond video freeze. So imagine that you are using this kind of RTC system and you are doing a future application such as remote surgery. This can not only be a frustrating user experience, but it can also be very risky and dangerous. So that's the situation now. So how does this happen, or how do we frame this problem? We identified that the pacing latency as a key component in this study. So let me show you our evaluations on WebRTC. So this is on the left side of the data. In this figure, we broke down the latency component into different partitions. On the left side of the data, that is for most of the cases when latency are lower than 50 milliseconds. The different components don't show much difference. But if we're taking a look at the latency that are greater than 200 milliseconds, or those tail cases, we found that the pacing latency is now taking the lead. And other components, such as like encoding, decoding, and transmission delay, they contribute to less than 1/3 of the total latency. We also validated this in the data we collected from the ByteDance code in cloud gaming, and we got similar results. The pacing latency significance contribute to 100 millisecond stores. So here I raised a question called pacing latency. But what this is, I'll talk about it more detailedly. Now, let's talk about what pacing latency is. So this is the sending pipeline of the RTC. There are two important components here. One is rate control, the other is video encoder. So ideally, the rate control constantly observes on the network, and it finally determines a rate. And this rate will be set as a target rate to the video encoder. So the video we are going to transmit will finally be compressed and segmented into media packets and sent over the network. But what's tricky here is that the data produced by the video encoder comes in bursts. So that is actually a quite natural thing. Because in the context of RTC, not like video streaming, the video encoder can only capture the video frame by frame. So we can get the output data frame by frame. So the data was produced in bursts. Like for example, if we're streaming video at let's say 30 FPS, there is a burst every 33 milliseconds, as shown here. So this burst can be big. We can do a math. So if we are streaming a 30 FPS video at 30 Mbps, a single frame can be as large as 100 packets. That's a lot. What makes these things worse is that we'll have the video content complexity virus. Think about the real video frames that we are going to transmit. Like the example here, the third frame is absolutely so different from the first two frames. So it calls something. The information density in the third frame is much larger than the previous two frames. So that will finally result in larger frame sizes. If we send this burst directly into the network, it is considered risky. It can overshoot network buffers. To overcome this problem, a very straightforward solution is that we just add a queue in the transport layer. And we set the target rate we just mentioned to the output data rate of this queue, so that the data can be transmitted very smoothly into the network. So in WebRTC-like framework, this component is called pacer. That sounds good. But why the pacing latency now is dominating? Because pacing delay is actually a queuing delay. As long as it's a queue, it will have delays. And what we found in this study of the first reason that why pacing latency is dominating is that the RTT is now shrinking. Let's first take a look at what level the pacing latency is in. Still, the 30 FPS example, we have the frame intervals of 33 milliseconds. And the pacing latency for average size frame, or a frame that follows directly to the target rate, will have a pacing latency of 33 milliseconds. Another example is a double-sized frame. A double-sized frame will have a double pacing latency, or in this case, 66 milliseconds. So we now get a takeaway here. The pacing latency is at the level of frame intervals. And now we know another truth, is that the RTT now shrinks to the level of frame intervals. Consider that in the past, when the RTT is about 200 milliseconds, the pacing latency will not take the lead. It's just a small proportion in this combination. But now, thanks to the edge service, the networking infrastructures, development, we know that in a lot of RTC applications, such as cloud gaming, the RTT has been reduced. The median RTT is about 20 milliseconds, the pacing latency will take the lead. So that is how pacing latency is drastic in nowadays situation. And another intuitive solution to this question is that, can we just let go these burst difference? Let's imagine that. If we just send it, the queue will not be formulated in transport layer, but be formulated in the network layer, the in-network buffer, right? So it will be the comparison of these two queues. If the pacing rate is less than the network bandwidth, so it will be better to let go these bursts. But the queue size in the network is very unpredictable. If we send frame burst larger than the queue, it will overshoot the network buffer. So we'll have the packet loss. And the retransmission followed by this packet loss will finally let the latency go to tail. So thus, either of these ways are not working. And the problem we identified is that the lack of the management to the burstiness. So in this work, we proposed ACE. We are going to manage the burst from both the in-queue and DQ perspective. So in-queue perspective, in-queue here actually means the encoder side. So we want encoder to produce less large frames. And the DQ perspective means the sending of the pacer. We want the data we transmit in the network to be a controlled pattern so that the burstiness can be managed by us and we can achieve optimal performance. So that is the high-level idea of ACE. Let's start with the pacer side or the transmitter side. Our core idea is that we want to adaptively control the burst size. So currently, there are two transmission schemes. Actually, I just mentioned. So the first one, we use the burst descending, and we'll have a risk of overshooting the network buffer, and the latency will caused by the retransmissions. But if we do the pacing sending, such as WebRTC does, we'll have a possible extra queuing delay, and the latency will caused by pacing. So both of them, we don't think they are good. And the reason for that is they have the fixed level of burstiness. That's not something what we want. And what we want is adapting between. So in ACE, what we propose is we control a bucket size of a token-based pacer. A token-based pacer basically means a token bucket here. So a token bucket allows burst, right? And we control its core parameter, the bucket size, so that we can determine the maximum burst value that we can send to the network. So how do we decide the right bucket size? Ideally, we want to know the network's available queue size so that we can know how much data we can burstily send in. But this is impossible to measure directly. So instead, the only thing we estimate is the current network queue sizes. And we adjust the bucket size according to this current queue size. When the network is relatively stable, for example, low loss, and the queue is not detected, we'll increase the bucket size to allow larger bursts. The purpose of it is to reduce the latency. And when loss occurs, or we sense a queue is building up, then we will decrease the bucket size to avoid overshooting. So this is a very simple control loop to address this problem. Simple, but very efficient. We also have another design on the encoder side. So our goal is to make the encode produce frames have larger frame size or less oversized frames. Actually, we have some existing solutions to address this problem. But what's in common for these existing solutions is that they perform a strict encoding rate control method. And what they do, in fact, is they perform more lossy compression. And that will result in a worse quality. That is also something we don't want. We have an evaluation experiment to show that a strict rate control method inside the encoder reduces the VMAP quality for 10 to 15 points. That is unacceptable to us. So instead, our insight here is to adapt the encoding complexity to enable a smoother stream. So let me explain the logic. The encoding complexity is actually determined by a sort of encoding parameters or technologies or techniques. The more advanced the video encoder techniques we are using, will result in a harder encoding complexity and a smaller frame size. While higher encoding complexity increase the encoding delay, the smaller frame size reduce the pacing latency. So there is a possible trade-off here. If increasing the encoding time by a small amount can lead to much larger reduction in the queuing delay here, the total latency can decrease, and we'll have a time saving. So we finally select a sort of encoding complexity parameters to control the complexity. And I'll introduce how we implemented and how we test ACE. We implemented our system in both the WebRTC and a widely used encoder called X264. And our main evaluation is performed through Mahi-Mahi emulations. We use real-world network traces from both Wi-Fi and cellular networks. And we compared ACE to some of the encoding approaches that I just said using the strict rate control method and some WebRTC-based method, such as using the bursty sending scheme or pacing sending scheme. We evaluate the VMAP score for video quality and a 95 percentile latency for the delay. And that's the result on the right. For the strict bitrate follow encoding method, it achieved the lowest latency. But by compressing these frames harder, the VMAP score of it is the lowest. And what about the WebRTC-based solutions? So it uses pacing. So we'll have the fluctuating frame size, but it will be smoothed by the pacing. In that case, the quality of it is the highest, but will have also the highest latency. But instead, ACE can manage between those and balance between those, so we get a good result. In conclusion, compared to the best quality baseline, we'll have a 43 latency reduction with almost no VMAP score loss. We also have more evaluations on loss rate, link cloud utilizations, parameter sensitivities, fairness, and you can find it in the paper. We also have 2 supplementary experiments to validate that ACE can be deployed in the real-world performance. The first one, we tested it on the campus Wi-Fi. We compared ACE with Baselines and Google Meet, a commercial app, and ACE can outperform them in both latency and quality. We also integrated part of our design, the pacer module, into the ByteDance RTC system and compared to the existing pacing and bursting baselines. In the emulation environment, ACE reduced the latency by 15%, and we also have improved the frame rate. Finally, let's see the takeaway of today's speech. We proposed ACE, and we propose to manage the burstiness in real-time communication. From the encoding side, we propose to selecting encoding complexity parameters, and that can result in a smoother bitrate. And in the sending side, we propose to use adaptive pacing and bursting switching sending. In that case, we can better utilize the bandwidth. And our evaluation demonstrates that we have satisfactory improvement, that the end-to-end delay can reduce up to 43% without any quality degradation. And that's all for today's presentation. Our code will be released on GitHub. Please scan the QR code to access it, and we'll also have some other improvements, possibly other works, but we'll all release that in this GitHub repo. So stay tuned. Thank you very much for listening.
Thank you very much for the great talk. I have one question. Why this is only working for RTC? Because for VOD, we also have kind of bursty. For example, when App Store happens, a lot of activity happens, right? Does that mean the granularity would matter? Because in VOD case, probably it's in hours or you know.
Yeah, I think that's a good question. But that for me is like first and after question, because I'm firstly working on RTC and I solved this problem. But I didn't actually consider about how even if the work can also be used in like VOD and video streaming. So I guess the answer is yes.
Thank you for the talk. It's very nice set of arguments you put forward to justify your solution, but I'm a bit confused because pacing is a form of congestion control.
Yeah, it's
right?
like part of congestion control, right?
Yeah.
Yeah.
So, and I think all these WebRTC solutions running on top of Google congestion control and so on, so they were supposed to already shape the traffic. Maybe not with a leaky bucket like you did, but there should be some impact of very congestion control. And if you basically remove it, congestion control, allow transmit bursts.
Sorry.
Maybe you can answer this one. Yeah.
I'm not actually removing any congestion control. So the congestion control is there, and it's actually GCC, right? So this actually determine a target rate. And the frame produced by the video encoder will have data fluctuating around that bit rate, right? And I just control those tiny bursts, whether it can be sent out or not. So in the large time scale, the rate is still the rate determined by the controller's control.
Yeah, and somewhat related to it as well, because I think in the classical congestion control, there have been results that actually pacing can be detrimental to the throughput, right? But there is a reason why you want to limit the transmission as well, because if you transmit a burst, like in famous paper talking about decongestion control, if you just blast all your data you have through the network, your throughput will improve. Just I'm wondering how fair you are to the rest of the traffic. Yes, you allow these bursts to go through, but you don't consider the impact on the cross traffic in the network. So maybe this burst will actually create queuing and make the latency performance worse for the other flows.
Sorry. What's the question again? Sorry.
So the question is, you allow the burst to go out into the network.
Yeah. So
Yeah,
in the short time scale, it's an overshoot of congestion control, right?
Yeah, it's overshooting and it can hurt other flows. So this particular flow, this RTC stream will get more throughput and get more information by the end of the frame, but the other applications, they will see the queues in the network that otherwise they would not see.
Yeah, so this, we know that, and actually it's like a tiny part of the congestion control we are controlling. So that's why we also evaluate the fairness, the issues to demonstrate that we won't influence other streams, things like that.
Okay, thank you. Let's thank the speaker again.